for production of ethene feedstocks of 99.95% purity required for polymerization reactors, cryogenic distillation columns operated at high pressures and high reflux ratios are commonly employed for large-scale separations of mixtures of ethene and ethane. Many MOF developments have targeted ethene-ethane separations with the objective of eventually supplanting the energy-intensive distillation technologies. Most of the MOFs that have been developed selectively absorb the unsaturated alkene by exploiting the pi bond interactions with extra framework cations in zeolites such as NaX or LTA5A, or interactions with open metal sites of MOF74, copper BTC, etc. In a different kind of an approach using UTSA280, the saturated ethane is practically excluded from the pores due to subtle geometrical differences between ethene and ethane. A completely different path to ethene-ethane separations is to use MOFs that are selective to the saturated alkane. In this presentation, I asked the question whether I should proceed my development activities along these lines, in which I have preferential uptake of the unsaturated alkene, or should I continue my developments in searching for MOFs that are selective to the saturated alkane, keeping in mind that my objective is to produce polymer grade feedstocks of 99.95% purity plus. This presentation is a follow-up to my previous presentation on C2H4, C2H6 separations with MOFs that is uploaded on my YouTube channel. I begin the discussions with examining two MOFs that selectively take up the unsaturated ethene. Let's compare the separations of 50-50 mixtures of ethene and ethane using two different MOFs, iron MOF74 and UTSA280. The breakthroughs for 50-50 mixtures are shown here. The y-axis represents the dimensionless concentrations at the exit, and the x-axis is a modified time parameter in which we plot the time multiplied by the volumetric flow rate at the inlet in liters per second, typically at STP conditions, divided by the mass of adsorbent in the bed expressed in kilograms. The two different breakthroughs are shown here. Red symbols indicate the breakthroughs with iron MOF74, and the green symbols are the breakthroughs obtained with UTSA280. There are important differences in the two breakthroughs. The most important one is to note that with the size exclusion of 280, in which the ethane is practically excluded from the pores, the breakthrough of ethane occurs practically near the start of the breakthrough run. On the other hand, With iron MOF 74, the uptakes of both components are significantly high, and the breakthrough of the saturated ethane occurs at a much later time than with UTSA 280. These have important consequences for a PSA scheme used in practice to produce ethene of the required purity, typically 99.95% plus. Let us compare the separations of 50-50 C2H4, C2H6 mixtures using two different MOFs, iron MOF 74 and UTSA 280, using a simplified PSA scheme in which we have an adsorption phase followed by countercurrent vacuum blowdown. The breakthroughs shown here are simulations using experimental data on the unary isotherms and diffusivities that are chosen to match the breakthrough experiments shown in the previous slide. With iron MOF 74, both components have finite uptakes within the 11 angstrom hexagonal channels, whereas with UTSA 2.8, the saturated alkane is practically excluded from the pores and gets rejected into the gas phase immediately after the feedstock is injected. The adsorption cycle is terminated at the times shown by the arrows here before the unsaturated alkene starts to emerge from the exit. So the adsorption cycle is terminated at these times. If we examine the component loadings of ethane, shown by the dashed lines, and ethene, shown by the continuous lines, in the two MOFs at the end of the adsorption cycle, we note that with UTSA 280, practically no C2H6 is remaining within the pores after the end of the adsorption cycle. However, with iron MOF 74, a finite loading amounting to 0.5 moles per kilogram of the saturated alkane remains within the pores at the end of the adsorption cycle. Let's look at the countercurrent vacuum blowdown operations. Here I apply deep vacuum corresponding to 2 pascals in the exit, and the cumulative moles of ethene, shown by the continuous lines, and ethane, shown by the dashed lines, are during the blowdown operation are plotted here for the two MOFs. There are important differences in the C2H4 and C2H6 recoveries in the blowdown phase. With UTSA 280, the there is only a very small amount of C2H6 that is desorbed along with the desired C2H4. However, with iron MOF 74, the C2H6 that remains within the pore space at the end of the adsorption cycle is also desorbed concomitantly with the C2H4. And this co-desorption of C2H6 along with C2H4 has severe consequences on the purity of the product that is recovered in the vacuum blowdown operations. The percentage of C2H4 is plotted for UTSA 280 and for iron MOF 74 by these two lines. We note that with UTSA 280, the maximum purity in C2H4 is 98.5%, whereas with iron MOF 74, the maximum purity that is possible in the simplified two-step adsorption-desorption scheme is only 88%. So the summary of the differences between these MOFs is obvious. With iron MOF 74, we have higher productivity of C2H4, but the purity of the recovered product is only 88%. With UTSA 280, the productivity of C2H4 is significantly lower, but the purity is significantly higher. A more complex 5-step PSA scheme is required in order to increase the purities beyond the levels indicated here. But from my own calculations, it appears that the achievement of 99.95% purity is near impossible with either of these two MOFs. Therefore, let us see whether this situation can be remedied by choosing a C2H6 selective MOF. Let us look at the C2H4, C2H6 separations for 50-50 mixtures using CPM733 as described in this paper published in JACS in 2020. The MOF is selective to C2H6, and therefore C2H4 is rejected into the gas phase and can be recovered in nearly pure form during the adsorption cycle. If I plot the purity of C2H4, percentage C2H4 in the outlet gas as a function of this modified time parameter, I note that it is possible to achieve 99.95% purity, but the productivity is only limited to this time interval. In order to increase the productivity, we need to continue MOF developments in order to improve the C2H6, C2H4 selectivity more in favor of the unsaturated alkane. But the message that emerges quite clearly from this slide is that it is indeed possible to achieve 99.95% plus purities using C2H6 selective MOFs, and future developments must proceed along these directions with the objective of trying to improve the selectivity in favor of the saturated alkane.